In calculus, finding the tangent of a curve is intuitive. We differentiate a function to find its instantaneous velocity. But what happens when we reverse this process in a multidimensional space? How do we integrate a vector to find its total accumulation? To answer that, we look at vector-valued functions. These are mappings that take a single real parameter, usually representing time, t, and output a coordinate in a multidimensional space, rk. Finding the instantaneous velocity of this function is a matter of differentiating it component by component. At any point along the curve, the derivative gives us the exact direction and speed of the particle. The inverse problem is more elusive. If we are only provided with this continuously changing velocity vector, how do we calculate the total displacement over time? In standard calculus, we visualize integration as the area under a curve. However, in three-dimensional space, there is no immediate physical equivalent to that area. Defining this integration provides the formal framework needed to model motion in classical mechanics, analyze field lines in electromagnetism, and define curvature in differential geometry. To move forward, we need a way to bridge the gap between multidimensional motion and the one-dimensional logic of the integral. Definition 6.23 establishes that the integral of a vector-valued function is a vector containing the individual scalar integrals of its components. This implies no new operation is required. We simply apply standard Riemann-Stieltjes integration across multiple independent axes. We visualize this by breaking a three-dimensional vector into x, y, and z components, plotting three separate two-dimensional line graphs. Accumulation occurs independently across these axes. We take those scalar totals to form a single final vector in space. This component-wise approach works because it respects the linear structure of the space, treating a complex multidimensional problem as simultaneous scalar calculations. This structural consistency allows the fundamental theorem of calculus to function in multidimensional spaces. Theorem 6.24 shows that the integral of a derivative still yields the net change in the original function. The prerequisite is simply that capital F must be the exact vector-valued antiderivative of our function lowercase f. If we define lowercase f as the velocity of an object, then capital F represents its exact position in space at any given time. Integrating this velocity from A to B allows us to bypass the specific path taken, calculating net displacement. The theorem reduces all intermediate velocity data to a single vector connecting the start and endpoints. Theorem 6.24 demonstrates that the relationship between instantaneous change and total accumulation remains consistent, regardless of the number of dimensions involved. This logic also extends to physical boundaries. Theorem 6.25 formalizes the relationship between the magnitude of an integral and the integral of a magnitude. The left side of this inequality represents the magnitude of the final integrated vector, which is the straight line displacement between 2 points. The right side represents the integral of the speed, which calculates the total distance traveled along the actual path of the curve. This strict mathematical inequality serves as the formal, rigorous expression of a deeply fundamental geometric truth that we experience every day in the physical world. Your net displacement can never be greater than the total distance you physically traveled along the path. Theorem 6.25 ensures that the formalisms of calculus adhere to the geometric law that a straight line is the shortest distance between 2 points. To prove this inequality, Rudin uses an algebraic approach that avoids the complexity of coordinate-based geometry. He begins by defining a constant vector, y, representing the final value of our vector integral. He calculates its squared magnitude via a dot product. Because y is constant, it moves inside the integral, making the dot product the new integrand. This move allows Rudin to apply the Cauchy-Schwarz inequality directly to the function inside the integral. Cauchy-Schwarz guarantees that this dot product is bounded by the product of the magnitudes of y and f of t. By placing this upper bound back into the integral, the constant magnitude of y can then be factored back out. After canceling the magnitude of y from both sides, we are left with the exact inequality we sought to prove. Through the Cauchy-Schwarz inequality, Rudin establishes this geometric reality using the efficient, rigorous tools of linear algebra. These proofs are more than academic exercises. They are the tools required for engineering and physics. Vector integration allows us to solve the differential equations that govern the flight paths of projectiles and aircraft. It is the language used to map the strength and direction of magnetic fields as they move through complex spaces. In fluid dynamics, integrating these velocity fields over time is how we track the flow of water and air in real-world systems. To summarize, vector functions integrate component-wise, preserving multidimensional linear structure. This allows the fundamental theorem of calculus to naturally describe physical accumulation in higher dimensions. The integration of vector-valued functions provides the necessary mathematical framework to analyze motion, geometry, and multidimensional systems. If you want more deep and structured explanations from books like Rudin, including every theorem, proof idea, and example, don't forget to like, subscribe, and continue your journey into higher mathematics.